In this lesson, we are going to learn how to solve a comprehensive electrochemistry problem. But before we start on this type of problem, we need to write down this two information right here. Leo the lion says grr, and ox red cat. Why is that important? Leo lose electron in oxidation and gain electron in reduction. And the location of oxidation is in the anode electrode, and the location of reduction is in the cathode electrode. What does that mean? When this part right here, when we have reduction in the cathodes, you would say that it gains electrons, okay? And when you gain electron, those gain electrons are going to interact with the metal ions. Of course, that would result in gain in mass. So keep that in mind, okay? That's all you need to know when we're starting any electrochemistry problem. So let's go back to this problem. An electrochemical cell is constructed with an opening switch, which we know is right here. Okay? In the diagrams above, a strip of Sn, which is tin, and a strip of unknown metals, X, is used as electrode. So we have two electrodes. In this case, this is tin electrode, and this is the unknown electrode. Okay? When the switch is closed, the mass of Sn, tin electrode, increases. And right away, this is extremely important because if this mass increase, we know that Sn must be where reduction occur, and that's where the cathode's gonna be, okay? And then we have our half cells. So we can now start identify our half cell. We just learned that the mass increase in Sn electrode, this must be reduction. So therefore, this must be oxidation. But notice how this is given in terms of reduction. So we have to switch it, okay? So keep that in mind when we have as we continue our problem. So in the diagram above, label the electrode that is cathode, which we know is gonna be right there, Sn. So that would be your cathodes. And how do we know, based on the justification, based on the fact that reduction gain electron, so you can write something, reduction gain electron, and the gain electron will interact with the metal ions, which will convert to metals. So that's how the mass is being added to the tin electrode. I'm not going to write it down. You write it down, okay? So again, because the mass increase in tin electrode, we know that reduction occurs because gain electron interact with the metal ions, and that metal ions react with the electron, and that produce solid metals on the outside of the electrode, which increase the mass, okay? Now, let's go back to the problem. In question B, in the diagram above, draw an electron, indicate the direction of electron flow in the external circuit when the switch is closed. That means we close the switch. So how does that work? Remember, electrons are lost in one place and it's going to a place that's being gained. So we know right away it has to go from here to there. So electrons are lost in this electrode right here, and it's going to follow the wire or flow through the wire, and it's going to end into the cathodes, which is where reduction occurs. So this is the flow of electron, where the electrons start from where lost, and it's going to continue into where it's being gained in the reduction electrode, which is cathode. Now let's look at another problem, and then you can just say, and for this answer, you just gonna write see above picture, or see diagram above. Now let's go to C. If the standard cell potential was E cell, very important, okay? So this is a combination of reduction and oxidation, and it tells you the E cell is 0.6 voltage. What is the standard potentials in volts for X with a 3 charge and X? So we don't know what is that specifically, but we know that for every E cell, okay, is equal to reduction plus oxidation. We know the reduction, or we know the E cell is equal to 0.60, okay? And we also know the reduction is Sn, which is negative 0.14, plus oxidation, which in this case is going to be X, because we don't know. Can we solve for X? Of course. X is equal to, we bring this over, that equal to plus 0.74. But again, this is oxidation. So when we express this in terms of reduction form, so if X in terms of reduction, we would have negative 0.74. Okay, so that's for in the reduction form. But in terms of oxidation, it will be positive 0.74. Now, why do we have to worry about in terms of reduction form? Because if we look at our table given on the AP test, all the half cells are given in terms of reduction. It doesn't give you in terms of oxidation. So that's why it's important. So let's go back to this problem. For D, identify metal X. Oh, look at that. Metal X. We can use this right here, which if we were to rewrite this in terms of reduction right here, of course it's going to be negative 0.74. So all I have to go back here, look at our table, find negative 0.74, and look at that right there, which is right here, chromium 3 plus 3 electron equal to or produce chromium solid. So right away we know that is metal X, which is X is equal to chromium. That's all we have to do. See, we look at the table into reduction form, negative 0.4, and that's chromium. And the next question is, write the balanced net ionic equation for the overall chemical reaction occurred in the cells, which just basically combine this. But before we do that, we need to express the reduction for the oxidation right here in terms of oxidation form. So we have reduction, which is Sn 2 plus 2 electron, and that produces Sn. And then for the oxidation, we know it's right here, which is chromium. But again, oxidation is losing electrons, so we do the opposite, which is Cr, okay, and that will produce Cr 3 plus 3 electron. To balance the chemical equation is about balancing the electron. Note how we have 2 and 3. So what's the common multiple? So we have to multiply this one by 2. We have to multiply this one by 3. And that will give us 3Sn 2 plus 6 electron and 3Sn. Where over here we have 2Cr, okay, and 2Cr 3 plus 6 electron. Now we combine them together. Note how the electron, one's on the reactant side, one's on the product side. They cancel each other out. So let me write some over here because we need more space. So I just combine them together. So we have 3Sn 2 plus, anything else on the reactant side? Right here, plus 2Cr, okay? And I'm going to draw the arrow. Down here, I'm going to write the product size, okay? Which in this case is 3Sn plus 2Cr 3 plus. Notice how the electrons are being canceled out. And this is our balanced net ionic equation for this chemical reaction. And what's the next question? The next question is predict the signs of delta G for the reaction and justify your prediction. And if we do that problem, we have to realize what is delta G equal to. We know that delta G is equal to negative N F times E cell. And what's N? N is the number of moles of electron being transferred. In this case, the balance equation tells us negative 6. In this case, the balance equation tells us that 6 electrons are being transferred. So N is equal to 6, okay? And F is the Faraday constant, or specific Faraday constant conversion factor. Basically, for every 1 moles of electron, there is going to be 96500 coulomb, or 96,500 coulomb internal charge per every moles of electron. But more importantly, if we just look for the signs of delta G, all we have to do is look for the signs of E cell. And it's given to E cell is positive. We take a positive times a negative. What is that going to give us? Of course, it's going to give us a negative. So that's pretty easy. We don't have to do any fancy problem, but it asks us to justify the prediction. So we just need to write down delta G equal to negative N F E cells, okay? And you can write something, because E cell is positive, and that time by negative will give us a negative answer. Or just to be easy, you just, for this question, to determine the sign of delta G, all you have to do is write down this equation, and you just have to write that because E cell is positive, so delta G must be negative. There you go, because you have a positive times a negative, give you a negative. Now, for the next question, calculate the values of delta G, which we just plug in. N is equal to your number of electron being transferred. But before that, we have negative. So if we go back to the equation, 6 is the number of electron being transferred. So we have 6. And what's F? F is the Faraday constant, which we know right here, okay? Which in this case is 96500. And your E cell, we know right here from this problem, is 0.60. 0.60, and we just plug it in. And we plug into the calculator, negative 6 times 96500 times 0.60. Give us negative 347,400. And that is our delta G. And the sign for delta G is joule. There you go. And then the next question asks us, is this reaction thermodynamically favorable? And justify your prediction. There are multiple ways. One way is that we realize that there is a pattern that we have to memorize. And that pattern is this, relative to this right here. It's basically when you have E cell positive, you would have a favored or spontaneous. When your E cell is negative, you have not favored or non-spontaneous. But in terms of delta G, we know right away, if delta G is negative, we would have favored. If positive, we have not favored. So you decide in terms of your justification, but I like to use E cell. E cell is positive. It's easy for me to remember. Positive potentials, which means more likely they have the potential to go through the reaction easily, spontaneously. So that's how I memorize it. So in this case, because E cell is positive, it is going to be favorable. So I'm going to say favorable or favor. Okay? And that's all. Or, just to be more specific, spontaneous. And then the next question is this. Whew, this problem's long. An electric current of 1.5 amps passed through the cells for 40 minutes. Calculate the mass in grams of tin that is deposited on the electrode. Now this problem becomes more complicated because in order to solve that problem, we need to use Q equal to IT. Now what's Q? Q is the charge in coulomb. I is the current in amps, which we have here, and T is in second, which is time in second. Here we have 40 minutes, so right away we need to convert that to second. But I take that minute times 60. So what do we have? Of course we're going to have a lot of seconds. Well, let me plug into the calculator. So 40 times 60, what do I have? I have 2,400 seconds. Okay, so that is your T right there. Now, let's plug this in the problem. But before we solve the problem, let's go back and look at the flow of information and the plan to solve this problem. Why do I care about this equation? That is because in order to solve this problem in terms of the mass of the metals being deposited, we have to solve for coulomb. Because here's the pattern. Because once you have coulomb, you can use the Faraday constant conversion factor, which is 96500 coulomb, equal to 1 moles of electron, to solve for the number of moles of electron. And once you get the moles of electron, guess what you can do? You can now solve for the moles of metal. And which once you get the moles of metal, you can solve for anything about that metal, which in this case, the mass of the metal. And where's the moles ratio going to be from? Of course, it's going to be from here, from the balanced chemical equation right here. You know how we have 10, and the balanced chemical equation tells us that there are 6 electrons being transferred. So we can say that there are 6 electrons for every 3 moles of Sn. So that's how we solve for it. So let's go back to the problem. So here I have the problem solved out for you already, okay? Here you have Q. I solve for Q, which is just your answer here. That's your time in second. Give us 3,600 coulomb. And once I get that coulomb, I can plug this in right there. I have my coulomb, time my Faraday constant conversion factor, because this coulomb, so the coulomb on the bottom cancel out, give us moles of electron. And looking at the balanced chemical equation right here, we know that 6 moles of electrons are being transferred for every 3 moles of tin. Okay? So we know that 6 moles of electrons are being transferred for every 3 moles of tin. And once we know the mole of tin, we just convert to mass of tin, which is from the periodic table. 1 moles of tin is equal to 118.71 grams of tin. And there you go. This is your mass in gram. And all we have to do is plug into the calculator, and we have that as our final answer. So in a way, it is extremely complicated, but if you know how to solve it, it is pretty easy. Okay? So always think about coulomb from Q. And there you can solve for moles of electron, or moles of metals specifically. And you can solve anything about that metal. And this is the most complicated question that you can get about electrochemistry problem.